Hey, good afternoon. Thanks for the introduction. I hope you're all enjoying your Ocean Hack Week so far. This is my first time ever participating. Wish I could be there in person. I actually was there just a couple weeks ago and thought it was beautiful. So hope you guys are getting able to get out and explore.
And you want to give us intro about yourself and your org?
That's the plan. Yeah, so my name is Ciara and I'll be presenting today on this project called Assessing Weather Model Skill During Extreme Events, NOAA GFS, which is the Global Forecasting System, versus SOFAR Spotter buoy observations during Hurricane Henri. Yeah, so I'm an early career data analyst at a small maritime technology company based in San Francisco, California. The company makes small mid-ocean buoys that are about 12 inches in diameter. We deploy those as part of a global sensing network, which we call our grid. You can see a visual of what that looks like here. At any given time, we have a couple hundred of these out in the water. And we actually use the observations from these buoys to ingest into an operational wave forecast model. And we actually ingest the spectral observations from these buoys. Using the weather models that we create, we actually use that to route and optimize the routes for ships. And you can see some of the operational output here. Yeah, so I also wanted to let you know that as like an early career data analyst, when I first started here at SOFAR, I was mostly involved in sensor validation. So just kind of taking a look at the sensors on board of our buoys and making sure that they were collecting and providing accurate measurements of the environmental variables that they're monitoring.
Hey, Ciara, can you zoom in a little bit?
Sure.
Thank you.
Can you see that now?
Yeah, you could even do a little bit more.
More?
Perfect.
Great.
Thank you.
Yeah, so again, I can't really see your faces. So if anyone has any questions, feel free to stop me at any point in time. But as far as the content of this tutorial, first, we'll primarily be querying data from two different data sources: point-wise data, which is the mid-ocean buoy data from our spotter data archive, as well as gridded data from an operational government forecast center. In this case, it's going to be NOAA. Once we identify and query these data sets, we'll subset them into for an analysis. And then we'll co-locate the point-wise data with this gridded data to assess the performance of in this case, NOAA forecast data during this extreme weather event. And then we'll visually and quantitatively compare the skill between the observations and the weather forecasts. So I've included a link here to how to set up your environment with required dependencies. I understand as part of this event that you should already have this set up, but if you wanted to revisit this content later, then you can do this on your own following the link here. So we'll first start with importing some of our Python libraries that we'll need to do this. As I understand, there were a couple tutorials earlier today on data access and Xarray, so I'll kind of skim over some of these parts, but otherwise, we'll be using Botocore and Boto3, which is used for querying data from Amazon S3, which is a cloud storage platform that hosts something called the Open Data, or Registry of Open Data, which is like an Amazon program to store data for free, publicly accessible. We'll also import a package called Cartopy, which is a geospatial mapping library, and so we'll use this to kind of make some plots at the end. We'll use another package called Datetime, which is used for dealing with timestamps and things like that. You might already be familiar with matplotlib, which is just used for plotting data, and we'll use this for things like time series. And then we have some other pretty standard packages for dealing with time series and arrays and things like that. And so that's NumPy. OS is for dealing with directory structures on your personal machine. Pandas is just in general for dealing with data processing and analysis. PITS is something for, again, dealing with, in this case, time zones as part of your timestamps that we'll be interacting with. SciPy has an interpolate module, and so we use that for interpolating some more data. And then we'll be really heavily relying on Xarray and XAR. So first, we're going to start by creating a directory to store all of the data that we'll be working with. And so this will be our spotter data and our gridded data from NOAA GFS. As part of this tutorial, we're most interested in the event Hurricane Henri, which happened during August of 2021. I chose this event because the SOFAR Spotter archive really only spans time period between April and March of 2019 and 2022 respectively, and so this falls right in there. But if you are interacting with this data and you did want additional time coverage, then you can definitely reach out to myself or go to our website and get additional access. I decided to just go with one variable for this analysis, and that's significant wave height, and that's generally a measure of how high the waves are at a given point in space and time. And I thought it'd be kind of a good analysis to look at what the conditions were like in the days leading up to Hurricane Henri's landfall in the US. So we'll go ahead and first start by selecting a time range of interest. And so we do want to be cognizant of how long we make this time, because it's important to think about how much data you're working with and like the constraints of your machine that you're working on. When using things like cloud compute, that's not as much of a concern. From there, we'll go ahead and create a date range. Oop, I don't think I actually imported my libraries. So then we'll create a variable called date range, and this is basically going from our start date to our end date and creating an hourly array. So this would start at August 21st, 0Z or 0 UTC, and then August 21st, 1 UTC, and there and so forth until your end date. And we do pick this array because the weather model data that we'll be working with has hourly output. And so increasing the frequency to like every half hour wouldn't necessarily make sense for this particular use case. But it's really important to check out the data that you're working with and understand like what time frequencies make sense for these kind of analyses. One thing that you could do is if you were interested in a longer period of time and certain parts of the day, if you're looking at diurnal behavior, you could increase this frequency to something like every 6 hours. But for this analysis, we'll go with every 1 hour. Next up, we're going to go ahead and load in our spotter buoy dataset. And so I want to navigate to what exactly that looks like. And so you'll find all the links that you'll need to do this tutorial are within. And so we can go ahead and click on the SOFAR Spotter archive on the AWS registry of open data. I really like to use these AWS links because for me personally, I'm a pretty visual person, and it's really helpful to be able to kind of like poke around and see what exactly I'm looking at before I start my analysis. There are other ways that you can interact with these AWS structures, like via the command line if you're comfortable using that, but I think this is a great place to start. One thing you'll notice is that you can see that there's a ZAR option and a .nc or netcdf option. And then we also have bulk and spectral data. Today we'll be interacting with the bulk data, and this is for variables like significant wave height and wave period, wave direction, things like that. And then the spectra will contain the spectral information, which is a little bit more detailed information about like the energies that particular buoys are recording. And all of these files are containing all of the global data for all of the spotters that were on our global network between 2019 and 2022. And so one thing that I did want to go over is also the differences between ZAR and netcdf. For me personally, I'm actually most comfortable working with netcdf data, but for this tutorial, that'll be cool to dive into ZAR since that's available here. It's kind of a newer data format that's making its way through like the earth science community. And I guess you can definitely do your own research on this, but to me, the biggest differences are within netcdf files, you have your actual data and your metadata. So this is information about like your variables and what units those variables are stored within this big data set. And as you can see, it can get pretty large, like this file here is 8 gigabytes. But it's not ideal when you're interacting with netcdf files. In order to work with it, you kind of have to download the entire file and then subset based on the analysis that you're doing. ZAR, on the other hand, splits up the metadata and the actual data so that it can be, it's called chunked, and you can interact with it without downloading your entire data set. And so it's able to do that through these directory structures. So we can go ahead and click on the bulk one to kind of take a look and see what this is like. So as you can see, there's some information about like your metadata, and this has like a finite set size, and then your variables, for example, are like further subset, so that ZAR can be, you can like interact with them in that way. Okay, so we'll bump back over to our notebook and go ahead and ingest that data. Make sure that you're running also all of your cells up until this point. I don't think that I had yet. I think, so you've already covered Xarray. I'm not sure if you went over kind of the different engines, but typically when you're interacting with NetCDF data, you don't need to always specify an engine, but with interacting with other data formats, you sometimes do need to specify the data format that you are looking at, just so Xarray knows what's going on. And so here I've specified ZAR. And I've entered in the data set so that we can kind of take a look at the structure. And as you can see, with ZAR, it's able to access this metadata and some of the different variables that are available through the Spotter data archive. And as you can see, we have like our coordinates, our time, and all of these other variables. And then today, again, we're just interested in significant wave height. Next up, we're going to need our gridded data from NOAA GFS. And so we'll go back up to the top and click on the NOAA GFS on AWS Registry of Open Data. When, again, dealing with gridded data and just like weather models in general, oh, interesting, okay. It's important to know what you're looking at and making sure that you're querying the right data, understanding whether or not there is temporal coverage for that data set. For example, I actually was wanting to use something called the ECMWF Error 5 dataset, which is run, it's a government organization in Europe, and this is a reanalysis dataset. So it's basically a weather model that's run for the past based on like all the information that we know now. And this is one that I really enjoyed working with, but when I actually went to go create this tutorial, I hadn't interacted with it in a while. And one thing that I discovered is that this dataset is actually deprecated. So when you are going through these analyses, making sure that the sources that you're working with exist and have like the temporal coverage you're interested in. AWS is really good at providing descriptions of some of this data, but you'll kind of, I think it's good to kind of go through the documentation that the actual government provides to better understand the data that you're working with. So in light of this deprecation, I switched over to NOAA GFS, and now we need to figure out what is the file naming structure of the data that we're interested in. As you can see, you first get transported to what's called this, so I guess I'll back up a little bit. So there's AWS, they have this cloud storage platform, AWS S3, and within S3, there are things called buckets, and buckets are data sources that are affiliated with like a given source. And so in this case, this is a bucket that is dedicated to NOAA Global Forecast System, or GFS data. But there can be a number of different data sets within that bucket. And one thing that we see here is you'll see this ENKF GDAS. I actually don't know exactly what this is, but my thoughts are that this is something that's called like an ensemble weather forecast model. And that's when you run a number of weather model forecasts, generate forecasts for like a given time, and you average those all together. And we're, for this analysis, just interested in like the regular one forecast, one init time, or one start time. And so we need to find what that data looks like. And if you go to the bottom, one thing that you could do is kind of poke through the different pages that are available. And you can see like what times are valid for this data set. But I've gone ahead and poked a little bit ahead, and sorry, my Zoom is covering my tabs. Okay, great. So as you can see, we started in this particular bucket for the NOAA GFS data. And then, yeah, we were just interested in the non-ensemble data, so just GFS. And so if I were to go back to the original bucket, I could search. Just gonna let it load for a second. Okay, took a minute, but as you can see, we have this regular GFS data, and that's going to contain all of our variables. So let's click on like a random time just to kind of get a sense of what the structure of the data is like. And you can see there's this 0, 6, 12, and 18. That indicates what's called the forecast init time. And so most operational forecast centers have a set cadence at which they create forecasts. The time at which they start running the model is called the initialization or init time. And for most places, that's on the hour, 4 times a day, every 6 hours. And so we'll go ahead and check out one of these. Let's go ahead and look at the 0th init time. Oh, fun. Actually, let's go to maybe something a little bit more. Okay, so there's a lot of stuff going on here. Again, there's a bunch of different data files, and so I'm looking for, none of these are necessarily speaking to me. This looks like some kind of flux variable, and again, we're just interested in significant wave height. I'm gonna cheat and go back to the notebook to see what exactly the name was for these different files. Okay, this is looking a little bit different than the example I was looking at, but I guess we'll go back a little bit. And what I was seeing before is when you go to the GFS data, and again, you have these hours, when you click on it, there's like a wave option and an atmosphere option, and we're interested in the wave data. And so feel free to go back and explore this on your own and look at for different data sets and things like that. But we'll go ahead and just download the data based on like the formatting and some of the like exploration that I did earlier. And also while we're talking about the S3 data storage platform, I also want to talk a little bit more about the structure. So I did talk about buckets and how those are affiliated with like a single source of data. Within your bucket, there's 2 other parameters that are really important, and that is your key and your prefix. The prefix is basically the path to your data set of interest within the bucket. And then your file name is, so the prefix is the entire path, and then your file name is like just that last level of your path. And the prefix does also contain the file name, but it basically tells AWS where exactly to find the data that you're looking in. In order to interact with the AWS platform, we need to set up something called a client. And so we do that with the Boto3 library. And it's pretty general. We don't say anything about our bucket, our prefix, or our file name at this point in time. We just set up our client with this line S3 client equals Boto3.client. And then we need to, from there, specify which bucket that we're going to take a look at. And in this case, it's the NOAA GFS bucket. From there, we're going to want to set up a local data path to store this NOAA GFS data to access it later, because this is not ZAR format. This is actually something called GRIB, which is very similar to NetCDF, but it's like an older data storage platform data file format that was used kind of more in the past, but the community has since transitioned more to NetCDF. And so we'll make our path and set up our directory locally. And from here, we want to set up our NOAA GFS prefix. And so this looks like GFS dot the init time of the model that we're interested in. And the hour of interest, which is associated with our init time. Again, we're interested in wave data and we're interested in gridded data. I can try to go back and explore that bucket later, but this is the format that I had seen earlier. And so we're going to be using a single init time, and this is going to be associated with the hour of our start date. And I believe that we set that to like 8/19/0Z of 2020 or 8/21 of 2021 0Z. And so we're going to use that single init time to determine which data files that we're going to be using. From there, our files, there's basically one file per hour for each like output, I guess. And so we actually need to construct then the file name because this will vary again for our date range. And our date range is 48 hours between the 21st and the 23rd of August. So I have this little function here that does that. And so we could have looked back at the AWS bucket to see what the format of these file names were to create this. And so you would want to modify this for other data sets. From there, we're going to iterate through all of the different hours in our hourly date range array and generate the file name for all of our files. Then we're going to attach that file to our prefix. And then we have like our full file name that I'm going to use when saving that data locally. And so then we're going to go ahead and download this data. One additional step that I add here is instead of just downloading the data and storing the file names, we're going to create this empty list here, list of model data sets that's going to store our data sets as like an opened file. And so we use this method xarray open data set to create our data sets. And as you can see, this is GFS wave model output. And so there are a number of variables stored within this particular file, but we're just interested in the wave data and it'll make it faster to work with if we just select this variable. So I've done that here with the variable name significant or SWH for significant wave height. So it looks like all of these files have been downloaded. I can verify that by going over to the left under this data directory that we've created, Node.jfs, and we can see that they're all here, or there are a number of files here. And we didn't get any errors returned from our data query. But let's go ahead and see what like one of these individual files looks like. So I've just put the path here, but again, we'll do something like name it example.ds and use our method. And again, we're going to specify our engine here. And you can go to the X-Rays documentation to see like what engine you should be using for whatever file that you're interacting with. Okay, so as we can see, there's has coordinates, a time associated with it, and all of these variables. So it looks like there's maybe wind speed, wind direction, components of the wind, significant wave height, and some other wave variables. But again, we're just interested in significant wave height, so that's all we've included in our big data set up here that is list of model data sets. So don't expect to find other variables within this later on. From here, at this point in time, we have like a list of all of these data sets that are associated with like a given time in our date range. And so to make it easier to work with, we're just going to concatenate them all together so that we have one big data set. And from there, we can slice in time, whichever times that we're interested in for analysis later on. Cool. So while that's loading, from here, we have, again, this massive gridded data set. That's our full NOAA data set for significant wave height data for the 48 hours. And then we also have our spotter data set that we ingested as a ZAR file. From here, we're only interested in, and again, both these data sets are global right now. And so we just want to subset them in time and space to just make the data set a little bit smaller and easier to work with. And so I've attached this graphic of Hurricane Henri when it was active a couple of years ago. And so we're going to use this to kind of determine the spatial bounds of our analysis and go from there. And so this is really helpful because you can see like the longitudes on the bottom and the latitudes that this was maybe relevant. And again, we were interested in the time before it made landfall. And so we're maybe interested in something around like 38 to 45 degrees latitude and like -80 to -70. But I've included some ranges down here. And so I ended up picking -80, -60, and then 25 to 45 for the longitudes and latitudes of interest, respectively. And so we'll go ahead and make sure that we have those variables loaded. I've also, we had originally set our start date and our end date earlier in the script, but we actually want to increase the bounds of those times to encompass our spotter data of interest, because we'll be doing something called interpolating. And so here I've set the time delta between the start date and when we actually like want to be looking at our data to about 30 minutes earlier. And then I've done that for the end date as well, but adding 30 minutes. And this is because if we have one aspect about the spotters that are on our grid is that while they do report hourly, they don't report on the hour. They basically start reporting from whenever the time that the unit was turned on. And so that could be like 12:15 p.m. And so they'll now report on like the 15th minute of every hour. And each of those spotters are reporting at different times. But in order to collocate our data, we're going to need to interpolate those spotter data in time. And so for the beginning of our date range, we're going to need to extend a little bit on either side for the start and end date to encompass interpolating to the hour for the first and the last hour of our date range. So now we're going to go through the process of subsetting our spotter data. We're just going to go ahead and run the cell first. It'll take a minute to load. And while that's loading, I'm going to talk a little bit about the data structure of the spotter data archive. Like I showed you before, there's like a netcdf option and a ZAR option. And the data within both of these data sets was structured to follow the global drifter, NOAA's Global Drifter Program or GDP data format. And what the format follows is a structure that is used as a convention within the netcdf community for something called trajectories. And trajectory data is used to describe any data set that belongs to a distinct path in space and time. And so this would be for any like drifting buoy, which is the case for global drifters, and for our spotter data paths as well. You could imagine that, I guess, so in this data set, we have a number of buoys that are present, a couple hundred, and they're all unique devices, but we have to store them. In this case, we store them all as a single file. You could see a world in which you have different columns associated with different devices. So in this case, the I would indicate like the index associated with one device. I2 would be the index associated with like another device, and the O's are the observations. And so these might be like 4 unique devices that reported at different times or like at the same time, but for different lengths of time. This can happen a bunch because every time we deploy these devices, they're not all going out at the same time and starting at the same time and ending at the same time. The nature of our deployments is that we send them out on these ships, maybe like 10 at a time. They get thrown overboard, they start reporting, sometimes they die. And so these durations of reports are a little bit different. And so one way we could store the data is like this in something that's called an incomplete multidimensional array representation. This is really easy to interpret because you can see that the different columns correspond to different devices and things like that. However, you can see there would be a bunch of missing values and all of this information would have to get stored and can quickly add up, especially for these really large data sets that are devices reporting every hour continuously. So we've used the netcdf convention of something called a contiguous ragged array representation. And so as opposed to different columns, these different devices occupy a number of contiguous rows within an array. And each of those rows corresponds to a different observation. And the contiguous rows are for different devices. Does anyone have any questions on anything so far, like especially the trajectory structure? No? Okay, great. So this is still loading, but I'll go ahead and describe what this cell is doing here. So first, in order to access the data in these contiguous arrays, we specify this variable called trajectory index, or traj IDX. And this is basically identifying, it's a variable to like identify the rows that are relevant for each of the different devices. And if we look down at the data format again, you can see that this could be a little bit difficult to work with. And with the way that the data is set up, we can't really select or like slice on different devices. And so what I've done is manipulate the data set to go from that array to a dictionary where each of the keys corresponds to a different device. And our devices typically have an ID that's like spot, denoting spotter, and then like a couple of digits after that. That is unique to each of the devices. And so what we'll do is we'll go through all of the devices in this coordinate of our data set trajectory. And so this contains the spotter ID. And we'll grab that spotter ID, slice our data set that was originally that like ZAR file that we had read from Amazon S3. Create a data frame, and we'll extract the information that we're most interested in, or that we need to do our interpolation or our collocation. And so this is latitude, longitude, time, and then our variable of interest, significant wave height. And then this should typically be the case, but it's always important to, if you're doing interpolation, make sure that your time is being sorted and it's like increasing monotonically or decreasing monotonically. And so we'll go ahead and do that here. Then we want to make sure that although we want to filter based on our times of interest. And so this is when we're going to grab our start and end times with like that additional 30-minute time delta from before. And then we're also going to filter based on the locations of these spotters to decrease the size of our data set. And then once that's done, this could exclude, and this should exclude a lot of the buoys that you're seeing here below. And so if none of those conditions are true, the length of this data frame should be 0. And so we're going to add a condition that's checking that as long as this length is greater than 1 and that there's data valid for the conditions that we specified, then we'll add this to our dictionary, with the key being the ID that's associated with this device. So it looks like it's done loading, and so we can move on to the next step, which is interpolating. And so we'll do this with X-ray. And so I've created a new list here to store the spotter interpolated data frames, because at this time, again, the data that we have available to us is the hourly data, but it's not necessarily on the hour. And we want to interpolate our spotter data to be on the hour to match the time array of our model forecast data, which is again hourly. So we'll go and iterate through the elements in our spotter dictionary. Identify our data frame, set an interpolation time. And so this will be on the hour. Interpolate for all those times. And then we want to, when we're interpolating, we need to do this not only for our variable of interest, we also need to do it for our coordinates, so our latitudes and our longitudes, because those will change as well. And so we set up a function with that SciPy package, interp1d, and we're going to use, there are different methods to interpolate, and these should have been the same, but they're not. So this should be linear for both. I've used linear here because we're looking at the Atlantic, and the longitudes in our region of interest are continuous, But if we were looking at spotters or like devices near a date line, for example, where there's a discontinuity in your longitudes, you would need to either use a different method here, like nearest, or implement logic to make sure that you're accounting for those discontinuities in your coordinates. And so we're going to go ahead and store those values in this new data frame. And so by the end of this, we'll have this mega spotter data frame that has information from all of your devices for all of your times of interest that have now been interpolated to be on the hour. Okay. And so then at this point in time, we can go ahead and do our co-location. And this is the part that relies heavily on the X-ray method for co-locating. And so we're going to go ahead and just add whatever the model value is at those given device locations as a new column. And we're just going to go ahead and set that to a nan to just be like a placeholder for the next steps. And so we'll then iterate through all of the times in our date range. So I could have iterated through our like PD.date range that we had specified a couple cells above. But just to make sure that we have spotter data that's valid for the time of interest, I've chosen to iterate through this mega spotter data frame timestamp and all of the unique times in it, because these times are repeated for any devices, for each device that shows up for our filtering. So then we need to also grab the corresponding data for this given time for the NOAA data. And because prior to this, it's again, this giant data set that's our 48 hours of hourly data. So we select our valid time. This is the name of the time dimension within the NOAA data set. And we make sure that it's in the right format that it's expecting. So at this point in time, the spotter time dimension has a different format than the NOAA data time format. And so we need to make sure those are the same. We're then going to filter our pandas data frame of our spotter data for this current time. And then finally, we can go ahead and interpolate. So the co-located values here are whatever the NOAA model values are at the spotter locations that are valid for this slice in time. And so we'll need to provide the latitudes and longitudes that we're interested in. And so these will correspond to, again, like the spotter latitude and longitudes. But if you're using like a different data set, like GDP, then you would obviously substitute this with whatever like the positions of that particular platform was. And so finally, we're going to add those values to that model value column that we added earlier for the relevant indices here. And then to calculate our skill, we're just going to go ahead and add another column. So at this point in time, we have our spotter data frame, and it has our spotter values for significant wave height, our interpolated model values for significant wave height at the spotter locations under model value. And then we also want to add a new column that's the error between the NOAA model values and the spotter significant wave height values. And so we do that here. So the goal here is to create, get an understanding of how the skill between NOAA GFS, how the skill of NOAA GFS evolves during this event over the 48-hour period. So we want to calculate the skill across all the spotters that were in this time and space dimension for each particular time. So there will be 48 hours total. And so we're going to do that by setting up an empty dictionary. And this will ultimately have keys that correspond to the valid, what's called forecast hour. And so this would be, if we're starting like at an init time, the forecast hour 1 would correspond to like the first hour after that init time, and so on and so forth. So we're going to iterate through all of our times in this mega data frame. We're going to specify our forecast hour, filter our spotter data frame, and then we're going to calculate the bias for all of those devices for that particular time. using this numpy.nan mean. And so we can go ahead and check out what this looks like. And as you can, did someone have a question? No, okay. So as you can see, we have this dictionary where we have the different forecast hours. So 0 would correspond to our init time. 1 would be the first hour after the init time and the second. And they each have a value that is associated with them that corresponds to this bias across all of the spotters in our domain. And so we want to go ahead and visualize that. First, I think it's important to get an understanding of where all of those devices were located relative to the storm of interest. So we're going to go ahead and plot some of those. So I'll run this cell here, and then we'll kind of take a look at the output so you guys can get a sense of what that looks like before I talk about it. As you can see, it looks like there were, I don't know, maybe like 20-ish devices that were reported in this particular time and space domain that we've selected. And I've decided to color them by their deviation, each of the spotters by their deviation from the model value. But this here is the model value minus the buoy value. As you can see, they're negative, so this indicates that the spotter value was larger than the model value. The background field, as you can see, is the NOAA forecasted significant wave height for this particular event without any processing, just to kind of show where the storm was and like the magnitude of the wave heights it was forecasting. And so we can do all that with this cell above. And I think it's important to, when you're visualizing differences over a period in time, to specify constant min and max values for your color bars. And so that way, when you're looking at the data over time, when you're seeing a certain color value associated with like a significant wave height, that magnitude isn't actually changing. It's the same when you're looking across different times. So we've done that here for both the spotter data, which is the C-bar min and max, and then for the background NOAA data. When plotting geospatial data, we also need to do something called like setting a projection for how we want to display this data. And so I've done this doing the Cartopy package that we ingested earlier. And so this is the particular projection that I've decided to use. And then we're also going to go ahead and make a directory to store all of our figures that we're creating. And so this data is valid for distinct periods in time. And so we're going to iterate again through all of our valid times for this 48-hour date range that we're interested in. And set some plotting parameters. We'll set up our figure and axes here. And we don't really want to look globally. We are just interested in this like particular space. So we want to make sure that we're also setting the extent of our figure with these few lines here. I think this was covered in the tutorial before this one, but X-Ray has like some really nice plotting methods that you can implement by just calling this plot method and then specifying where you want to plot it, your color map, and things like that. And then we want to make sure that we're plotting the order of your plotting matters. You can also like adjust this later, but we're going to plot the little dots that we're showing the errors between the buoy values and the model values second, so they get plotted on top and we can see them. And then we set some parameters about our color bar, and then that's what gives us these figures. And so we can kind of feel free to scroll through these and kind of take a look at some of the behavior of these errors over time and what they look like relative to their position to the storm. And as you can imagine, the storm is located where we have the higher significant wave heights, where darker red indicates these higher magnitudes for the significant wave height. As you can imagine, it's pretty hard to kind of pull out any trends by looking at one forecast hour at a time. And there's so many devices to look at that it's hard to make, I think, any conclusions about what we're seeing between the model differences and the buoy observations during this period in time. So from here, we're going to go ahead and plot a time series of the skill that we had calculated earlier, so the bias. So we do that, and this, okay. We're just gonna wait for this to finish. Any questions about the plotting or anything? Also, I understand that I'm technically close to the end of the hour. Yeah, so just want to get a sense of time too, on if there will be something starting right after this.
Ciara, no, we don't have anything else after this. We started a little bit late, so no big deal if it goes a little over.
Okay, great. Okay, I'll try my best to run and explain this cell while it gets bumped down. But this is pretty much just plotting like a regular time series of our skill. And again, these are values that are stored in that dictionary where we have a key that's the forecast, the valid forecast hour for the model, and then the corresponding bias, which is calculated across all of the spotters or the buoys that we see in our area of interest. And so we'll run that here. And so again, we'll need to set up a new figure and axes to store that information, make sure we're setting our title and axes labels appropriately so we understand what we're looking at, and plot. And so as you can see, we have our time series here, and all that information is shown. I would say looking at this, that there appears to be like some kind of trend where the magnitude of the bias decreases over the given time range. And can anyone say what this means about like the model, predict the model values versus the buoy values, as far as like their ability to predict the conditions that were present in this storm?
As the storm dissipated, the buoys and the model agreed more. So one of them has trouble predicting or measuring higher wave activity.
Yeah, exactly. I would have like the same takeaway as well. And so yeah, you can definitely play around with different skill metrics to go about this analysis. So that's kind of like the extent of the actual tutorial content, but I had some food for thought here. I also wanted to pose the question of what factors do you think might be impacting the calculation of our bias at our different valid times, so the different forecast hours during our analysis? Okay, no takers. Well, one thing that we did do was interpolate, and we linearly interpolated. And so technically, yeah, some loss of information can happen by trying to interpolate to like a given time between two transmission times of like a spotter buoy. And so that might be resulting in like some contribution of the bias values that we're seeing here. Any thoughts on how one would change this analysis to determine like which factors are most impactful for predicting conditions during this particular event? I guess I can give a suggestion. One thing that came to mind is for any given weather forecast model that you have, they have a resolution, a spatial resolution that they are valid for. And so for some models, this can be like pretty spatially large, and for others, it can be like a finer resolution. And typically, finer resolutions provide better estimates of, or can like lead to better estimates of conditions, especially for these extreme weather events that are pretty constrained in space and can vary significantly even within like something called a grid cell. And so that would be the constraints set by your coordinates, like your latitude and longitude values. So from here, I've given some suggestions as far as opportunities to play around with some of this content. but just kind of generally want to go over some of the challenges that I experienced, and things to think about when going through like these analyses when you're comparing observations to model data. One of the big ones is that variables can be named very differently between the observation data set and your model data set, and even between different models. So for example, if I was able to use the error 5 reanalysis data set, they might call their significant wave height variable like HSIG, but GFS calls it SWH. And so it's important to really go through the documentation and understanding what exactly you're comparing. Another thing that we did, again, was subsetting our data. These data sets can be really, really large. So to make them easier to work with, and especially when you're sharing some of the results in contexts like these, it's important to filter whenever and wherever you can. You also want to be consistent and aware of the different times that you're using. Again, the spotter data had like a different format for their time convention as opposed to the model data, and so we have to make sure that we were converting so that you could go ahead and do like the selecting based on the times from your other data set. You also want to make sure that you're using the same time zone. Those can be really, really sneaky and give you like results that are inaccurate for your assessment. We did also convert our longitudes before they were, I think, -180 to 180, but do some of our analyses, it was easier / the model data, I believe, was 0 to 360, so we had to go ahead and do that that conversion. Another thing I ran into was it had been a long time since I had set up like kind of a virtual environment from scratch. And so ran into some problems where even though I had imported the main Python package that I was using for some of these analyses like Xarray, there are actually some other subdependencies that I had to go ahead and install to make sure that everything worked, especially with like the ZAR and the GRIB files. Again, like I said, I typically work with NetCDF, and Xarray works pretty well out of the box without some of those subdependencies, but just going through like Google search, figured out that I did need to install some of these other ones like ZAR and CFGRIB. And that's pretty much it. I've included at the bottom an appendix. I know I talked a lot about weather models, forecast hours, initialization times. It can get kind of confusing, so I've kind of included some dialogue here about it. But if you have any questions, please let me know. Again, I'm available sporadically today and tomorrow, so if you did want to give any of this a shot for like your projects or anything, and you're running into any problems, definitely feel free to ask me any questions.